Hello everyone, my name is Tingyu Cheng. I'm a third-year PhD student at Georgia Tech. Today I would like to introduce our project PITAS, which is a sensing and actuating embedded robotic sheet for physical information communication. Before I dive into the details of this project, I would like to thank all my collaborators, especially my supervisors at Georgia Tech, HyunJoo and Gregory Abowd, and also my supervisor at Reality Lab, Marcello, Giordano. So 2020 was a special year. We experienced this once-in-a-lifetime global pandemic, which not only causes untold human suffering and death, but also totally changed our social relationship. We are forced to get used to all kinds of digital online platforms till one moment that we missed the physical contact as before. We, as the material-driven interaction designers, we like to develop a new technology that can bring us back the tangibility and make us feel more connected. To guide our design, there are many existing inspirational work. For example, Tingyu talks about utilizing the pneumatic-based soft composite materials to build novel shape-changing interfaces, which integrates both input sensing and active shape output. There are also other types of soft material systems that try to deliver more specific information, like for wearable applications, or to mimic the skin texture changes to even express emotions. Physical telepresence showcased several promising examples of remote collaboration, including remote shape rendering, PCB board soldering, or object movement manipulation. PITAS is more aiming to provide a robotic sheet which could be widely available in electronics or craft stores, like copper tape or other craft sheet materials. Those who enjoy DIY making can purchase a roll and use as needed for different self-sensing and actuating projects. With these considerations, we propose PITAS, a sensing and actuating embedded robotic sheet for physical information communication. PITAS is a synthetic sheet, contains one phase transition layer and one sensing and heating layer. Upon reaching the boiling point, the phase transition material will transform its shape and reverse back when heat is released. For making the phase transition layer of PITAS, we first mix the acetone and the EcoFlex 0050. And similarly, we mixed the tube 602, which is a carbon nanotube filler, to the same type of silicone for making the sensing and heating layer. And we bond these two layers together by applying a quick-dry conductive adhesive. We would like to note that we used the same conductive adhesive for gluing the electrodes to the PITAS sheets and purposely chose a higher dosage for the carbon nanotube to mitigate the effects from the contact resistance increase. After obtaining the PITAS sheets, there are four associated cutting methods. The most intuitive way is to manually cut the PITAS sheets into the desired shapes, which has also been reported from the later user study session to be the most effective fabrication routine. On top of manual cutting, one can also choose a vinyl cutter or laser cutter for more digital fabrication tasks. We have also listed 3D printing as an optional fabrication method to directly 3D print PITAS materials. The ultimate goal for having PITAS is to deliver different kinds of physical information within the same space or go across multiple locations. We have included 4 different kinds of information, including shape, color, temperature, and texture, which are mainly under visual and tactile categories. The geometric deformation is the primary one that can bring visual information. One can choose to cut PITAS into various 2D shapes or layering different 2D sheets into a 3D artifact. The other visual information is from color change. The heating nature of PITAS made it a perfect system for embedding with thermochromic pigments. For tactile information, thanks to the great adaptability, we can simply add or modify the surface texture of PITAS for different tactile information delivery. Since PITAS is a heating-based system, the heating itself can also be utilized as a resource to deliver temperature-related information. On top of heating, the bottom conductive layer can also be used to sense users' input signal. And we have mainly adopted 2 sensing mechanisms: resistive sensing, which we can sense bending and stretching, and also capacitive sensing, we can sense touching, pressing, and sliding. To better showcase how we can utilize PITAS, we introduced 2 applications to highlight different aspects for PITAS system. Even PITAS aims to convey either visual or tactile information, but the information can also evoke an emotional interaction. For example, we have used the PITAS to make an artificial rose. When one touches the petal, the remote set can start to blossom with the color turning into pink from colorless, which can indicate the feeling of missing each other. Similarly, one can also share loneliness when the other side see the leaves dripping down and turning color from green to yellow. One key feature of PITAS is how easy and accessible it is for novice users. So this application is to exemplify the simplicity of PITAS fabrication method, that one can use scissors or a craft knife to cut PITAS into arbitrary shapes to augment everyday objects. Here we have shown how we can enable post-it note with different PITAS arrangements for different deformation. People can also imagine to use this approach to update the different work task progress with your colleagues in a more physical manner. We don't think limiting the imagination within the research team is enough. We would like to see how PITAS can be a simple but powerful platform to be used by different people. So we recruited 13 designers to gauge the accessibility and also the design space for PITAS. For example, one designer imagines that PITAS can be attached to the food dispenser of a dog, and the pet owner can remotely trigger the food dispenser to feed his pet. Or within the hospital environment, one patient can touch the PITAS-made ankle band to inform the nurse that he is in need of help. To better validate the performance of PITAS, we have also carried out a series of testing. We have first tested how the thickness of PITAS actuation layer can affect the bending performance. According to the results, PITAS with 3mm and 4mm layer thickness performed the best, while hitting the 5mm layer or beyond might be challenging. We have also tested how much force PITAS can deliver. We used the force gauge to measure the actuation force and achieved around 1.2 newtons for the 3mm thick samples. With these findings from PITAS, we have also observed several limitations. The first one is the actuation time. The current actuation time for a 3 cm by 1.5 cm sample can be from 20 seconds to 50 seconds, which is long. We imagine to increase the thermal conductivity of PITAS will be an immediate next step. The second one is that the current PITAS sheets are still made in our research lab. We envision in the future there could be a roll-to-roll approach to produce PITAS in large quantity. Also, the current driving voltage is still very high. We believe to further increase the conductivity of the bottom conductive layer will help to solve this problem. Before I end my talk, I would like to ask myself a question. Can we one day swipe on our table to move a pen remotely? But why do we need to do this? Can our environment enriched with physical intelligence bring richer interactivities that we have never defined before? Okay, so with this question, I would like to end my talk here. Thanks again for listening to my talk.